Hola, Team Bio. Sorry the screencast is getting to you so late on a Sunday afternoon, but here it is. Okay, so today's screencast is on chromosomal abnormalities. So in last week's screencast, we talked about an example of a chromosomal abnormality. Blah, blah, blah. We talked about trisomy, specifically trisomy 21, which is when a person has 3 copies of chromosome 21, and as a result, they have the phenotype, or they have the genotype of trisomy 21 and the phenotype of Down syndrome. There's also examples of monosomy, and that is when you only have 1 copy of a certain chromosome. That also leads to different, so for example, Turner syndrome is an example of a monosomy. People only have 1 X chromosome, or women only have 1 X chromosome. And it can have cognitive effects, and as well as sterility. But most chromosomes we don't see trisomies or monosomies of, because having either 3 copies or only 1 copy of a chromosome leads to spontaneous abortion of the fetus. Okay, so this is one type of chromosomal abnormality. Another type is an insertion or deletion of a portion of a chromosome. And now, to change, or I guess to, this is different from a point mutation insertion or deletion. So a point mutation insertion or deletion is just a single base pair that's been deleted or inserted, which changes, as we talked about, potentially the coding sequence of a gene, so that every codon from the point at which the switch was made is changed. But this is a large-scale insertion or deletion, or a large portion of the chromosome has either been inserted or deleted from the chromosome. And I'm going to give you an example of a certain type of deletion. So there's a syndrome called cri de chat. It means, if you speak French, you'll know this, cry of the cat. And it's called cri de chat because children that are affected with this have abnormal larynxes, so abnormal throats, voice boxes, and they have a cry, a baby cry, that sounds like a cat when they are born. Whoops, it's not de, it's cri du. Cri du chat. Okay, fixed. So, cri du chat is an example. Sorry, I'm making myself laugh with my own pronunciation of this French. Okay, so this is an example of a large-scale deletion of chromosome number 5. And I'm going to throw on a karyotype here so you can see that. So here you can see that chromosome 5, the top arm of chromosome 5, is truncated. It's broken off. It's not there. Or of 1 chromosome, 25. And here's another schematic of it. Okay, so as you can see here, there's a large portion of chromosome 5 that is entirely missing. So this is an example of, in meiosis, either in the mother or the father, the top of this chromosome broke off, and only this piece of the chromosome ended up in the final gamete. So when the baby, let's say this is from the sperm, fuses with the chromosome from the egg, we're missing a piece of information up here, and this has pretty large phenotypic consequences for the children. So first of all, as I said, they have this cry that sounds like a cat as they are, when they're infants. And other symptoms include feeding problems because they have difficulty sucking and swallowing when they're babies, low birth weight and poor growth, in part due to the fact that they have trouble eating. They have severe cognitive speech and motor delays, and often behavioral problems such as hyperactivity, aggression, tantrums, and repetitive movements as well. And they often have unusual facial features, including a small head and jaw and wide eyes. So just missing a small portion of this chromosome has pretty big consequences for the people affected. And again, as I said, mostly this is not an inherited disorder, but this is a spontaneous breakage of this chromosome. And so, for example, the father that donated this sperm with this broken chromosome is not affected with Cri du Chat. In most cases, there's a spontaneous breakage of the chromosome in meiosis, and this then gets passed on. Okay, so this is an example of an insertion, a deletion. I'm not going to talk about an example, or actually, yeah, I'm going to briefly talk about an example of an insertion. So Huntington's disease, Huntington's disease is an example of a chromosomal disorder in which a certain gene has a CAG repeat. So it's CAG, CAG. This repeat, which is in all of us, gets expanded in people with Huntington's disease. So it's the result of during crossing over. I think it was Jack who asked, how do chromosomes know? Well, basically, chromosomes pair up with similar chromosomes, but sometimes in the act of crossing over, one chromosome can end up with a little bit more DNA than the other, and it can cause that chromosome to expand slightly. So people with Huntington's disease, they've had a meiotic event that led to an expansion of this CAG repeat. And when it expands beyond, I want to say like 30 or 40 repeats, then they start to exhibit the signs and symptoms of Huntington's disease. Let me do some research and make sure I got that right. Okay, yeah, so people with fewer than 36 of these repeats, CAG, 36 times, if they have fewer than that, generally you don't have Huntington's disease. But if you have more than 36, you start to exhibit the signs and symptoms of Huntington's. And Huntington's is a really terrible disease. Basically, it's a neurodegenerative disorder that affects your muscle coordination and leads to mental decline and behavioral symptoms such as aggression and moodiness and loss of memory. And the onset is variable depending actually on the length of this trinucleotide repeat. If it's longer, the onset is earlier in age. But generally it sets in around 40 or 50 years of age. Okay, so another example of a terrible insertion within a chromosome. The last type of chromosomal abnormality that I want to talk about is a translocation. Whoops. And a translocation is when a piece of one chromosome breaks off from its chromosome and binds to another one. And we're going to talk about why this is an issue right now. Okay, so here's an example of a translocation. So we have two chromosomes here, chromosome 4 and chromosome 20. And what happens in a translocation is that a piece of, for example, chromosome 4 will break off of its own chromosome, and it will line up and anneal to chromosome 20, and then reciprocally, chromosome 20 will break off and anneal to chromosome 4. So you get these hybrid chromosomes that look something like this. And now, this looks bad, and it is bad, but not as bad as you might think. So a person with a translocation is generally totally fine. Because say this happened in a sperm cell, so then the developing embryo has this chromosome 20 here and here, and chromosome 4 here and here, but they also got chromosome 4 from their mother and 20 from their mother. So let's say this is a person. I'm going to put this in a cell. Okay, so this has become a person. They got this genetic information from their father and this genetic information from their mother, and if you look at this person, they have the full host of genetic information, meaning that they have all the information found on chromosome 4, so it's like they have 2 copies of chromosome 4, and they have all the information on chromosome 20, so it's like they have 2 copies of chromosome 20. The problem with for a person with a translocation is when this person goes on to develop gametes themselves. They get basically they have the potential to get unbalanced gametes. And I'm going to show you that in a second. Because, okay, so here's the problem. This chromosome has no true homologous chromosome to pair up with when it comes to my metaphase of meiosis 1, and same with this chromosome, because this guy has been divided, and this guy has also been divided. So this chromosome doesn't know whether to line up here or to line up here, and this one doesn't know whether to line up here or here. Okay, so let's talk about the potential gametes that can be made with a person who has a translocation like this. Okay, so the image that I have here is slightly different chromosomes, but you get the point. It's still the same thing happens. A piece of chromosome 21 has annealed to chromosome 14, so this person has one normal copy of chromosome 14, one normal copy of chromosome 21, and then this joined pair of 14 and 21. So, what are the possible gametes that this person can make through meiosis? Well, if this, if this segregates with this, so these two are pulled over to the same side, we'll create this gamete and then this funky translocated gamete. If these two are both pulled to the same side, then we'll get this gamete and then 21, this gamete. And if these two are pulled to the same side and this one's alone, we get a gamete with just chromosome 14 and chromosome 21. So let's look at each of these individually. This gamete right here created is totally fine, right? It has a normal copy of chromosome 14 and a normal copy of chromosome 21. And this is also a balanced gamete. It has a copy of chromosome 14 and 21. So even though it looks funky, it has all the genetic information right here. Now, moving over here, now we have a gamete with 2 copies of chromosome 14. Bad. This is a no bueno gamete. This gamete only has chromosome 21 and is missing entirely 14. So again, not viable gamete. This has just a copy of chromosome 14, no 21. Not good. This has 2 copies of chromosome 21 and a copy of chromosome 14. So this will lead to a gamete with Down syndrome. Okay, so let's look. Now we assume they're fertilized by a normal gamete. We get zygotes that one is perfectly normal. Another one, you have another balanced translocation. So this is, again, leading to a normal baby. This is an example of trisomy 14, which is fatal. So this fetus will spontaneously abort during development. This is monosomy 14, again, fatal. So this fetus will spontaneously abort. Monosomy 21, I'm pretty sure that this is fatal as well, so this will be an unviable fetus, and this will lead to trisomy 21, or a gamete with Down syndrome. So, of all of the different possibilities for children, only 2 of them lead to normal development for this baby. So people who have translocations can have kids, but the chances that their kids, that they might have to try multiple times because they have much greater odds of having a fertilized embryo that's going to lead to spontaneous abortion of that embryo. Okay, so again, coming back to the main point, translocation is generally not bad for the people that have it. They're usually perfectly normal, but it can lead to difficulties conceiving because, as you see, we get a lot of unbalanced pairs of chromosomes in this case of a translocation. Okay, that is it. Again, sorry for the late posting of this, but I hope you had a happy Sunday.